All right, so in this lecture, we'll continue with the operations research. It's operations research course, and we'll continue with the translation problem, which we had taught in our previous lecture series. So we had looked in our previous lectures, we have introduced the translation problem as a special case of a linear programming problems. And we had said that the various existing methods that we would treat would be based on a translation problem which is balanced, right? And therefore, we have introduced the translation tableau, and we have also determined the optimal solution, right? For the optimal solution, it's important to know that we have defined two main methods, that is northwest corner method and also the Borgel's approximation method in determining the linear solution, right? The initial solution. After initial solution is obtained, we want to find the optimal solution or the strategy that we must use to transport or allocate the various material that we are transporting. And here we did introduce the stepping stone method and also the MODI, that's the modified distribution method. So in this lecture, we shall look at what we mean by unbalanced translation problem and how should deal with it. What do we mean by degeneracy, right? We may have some routes which are prohibited. How do we handle that? Then we can also have multiple optimal solution, right? Then there's a special case of a maximization translation problem where we may be dealing with the profits in transporting from one source to the other. So how do we handle that, right? So stay with me as we go through this lecture. All right, so the unbalanced transportation problem, what do you mean by that? So in general, right, the transportation problems are unbalanced in the real world situations, right? Supply will either exceed demand or demand will exceed supply, right? So let's look at this example. So in our earlier example that we have treated in this series of lecture, we had mentioned that there were 3 sites, that are transporting to 3 destinations, right? So assuming that the site 3 will increase its demand from 60 to 90, right? Then it means that the total demand will increase to 310, and that's of supply will still remain 280. So let's look at this typical example. So since the total demand exceeds the supply, this problem is seen as an unbalance, right? So how do you handle it? We handle it by introducing a dummy supply to take care of the offsets or the difference. So this is how it is. All right, then the dummy supply or the dummy source is assigned a transportation cost of 0, right? Transportation cost of 0. So let's look at this example. So this is a typical example that we had treated, and we're saying that site 1, right, is delivering a total of 120 cements, right? Site 2 is delivering 80. Site 3 is delivering another 80, right? However, destination 1 or the demand 1 requests 150, demand 2 requests 70, and that of demand 3 now is requesting 90. So when you sum the various demand, you have 110 by 310 here, and when you sum the supply, you have 280, right? So because 280 is less than 310, we see that the problem is unbalanced, right? So we have to introduce a dummy site, right? And the difference, which is 30, is then distributed to that dummy sites. It's distributed from that dummy site so that it will balance the transportation problem for us to have our 330. Okay, for us to have our 330. So this is what we do. So now that the transportation problem is balanced, right? We can then solve by the previous method, that the stepping stone algorithm, the MODI, the VAM, and also the northwest corner. All right, we can now solve the transportation in that regard. right? However, again, if the supply also exceeds the demand, then it means that a dummy demand or column needs to be added to the tableau, right? And to take care of the difference, right? So let's take this example. So assuming now we have demand 1, right? So we have this arrangement 100, 70, 60, right? Then you see that our demand will now increase, our demand will decrease 100, 70, 80. So this one will give us 230, right? However, the supply has been 120, 80, and 80, which is 280. So 280, 230, there is a difference of 50. So we need to create a dummy column or a dummy demand to take care of that. And all the costs allocation will be 0, right? All the cost allocation in that dummy scenario or the dummy demand will be 0. The same thing too with this dummy supply. All right, so then what do we do? So after it is balanced, then we can then use any of our previous methods, right? All right, so what is degeneracy? What is degeneracy? Degeneracy is basically when we fill the occupied cells, right? We normally say that it's supposed to satisfy the m plus n minus 1. However, after filling the cells, we realize that it is less than the m plus 1 minus the m plus n minus 1 condition. So if that happens, then we'll say that the transportation has degenerates, right? So we have a degeneracy here. So how do we handle that? How do we handle that? So you know that when we are, handling the degeneracy, right? We need to, or in the northwest corner, anytime we fill the northwest corner, right? When we fill the northwest corner method, right? We mostly fill in the diagonal way, right? So we fill this, then we look at the column and we look at the row if we need to assign. So assuming we fill and we have m plus n minus 1, right, condition, right, not satisfied, right, then any of these cells, either on the column or on the row, can then be allocated a value 0, right? You can then allocate a value 0 in that cell. And if that happens, then we'll say that we have handled the degeneracy. Like for instance, in this case, when we have a problem of dummy and the supply moving in this form, so we have 100 here, we have 100 here. So when we saw, we have 1, 2, 3, 4. Right, 4. However, m plus n minus 1 is supposed to be 3 plus 3 minus 1, which is 5. So having 4, right, having 4 do not satisfy this condition. So we create, we allocate 0 here so that we treat it as a cell which is occupied. And if that happens, then we can have our m plus n minus 1 condition satisfied. And if that is satisfied, before we can now proceed to use any of our methods, right? So this is what we refer to as degeneracy, right? Also, while solving the problem, it may happen that the problem arises and we'll have degeneracy. Like for instance, in this case, we have 1, 2, 3, 4, 5 occupied cells, right? We have 5 occupied cells. However, if we want to allocate this cell, right, we want to do the we want to allocate this cell plus, right? That means that 30 moves here to plus, it moves here to become minus, it moves here to become plus, and closes the loop with minus, right? That is the stepping stone algorithm. So this 30 will move and it will be positive here. It will go and subtract this. So our next iteration will be this. The 30 moves here. So you see that now we have 1, 2, 3, 4 occupied cells, which do not satisfy the m plus n minus 1, which is 5 occupied cells. So what do we do now? We allocate a dummy, value, which is 0. And we can put the 0 here, or we can put it there, right? Anyway, so that we can continue our iteration, right? So assuming we put it here, then now we can see that it satisfies the m plus n minus 1. So we have treated the degeneracy. If that is done, then we can continue the transportation problem, or can continue solving the problem using any of the methods that we have introduced earlier. All right, so then we arrive at this tableau. All right, so assuming now we are dealing with prohibited routes. What do you mean by prohibited routes? Right, so in the real world, some routes may not exist. Like for instance, the road is under construction, it's not existing. At night, some roads are not safe to transport some materials or some equipment or some products. So at night, that road is not existing. So it's a prohibited route. So how do you treat it? So usually the cost associated with transporting is treated as high risky. So it's very high cost, right? So we'll use the big M, right, to we'll allocate a very big value in the cost, right? And if that is allocated, you see that it will not come into the solution, right? Because we are trying to minimize transportation costs, right? So when you are minimizing costs and the value is high, it doesn't come into the solution. And therefore, we use that to treat a prohibited route. What if we want to look at multiple optimal solutions? How do we detect it in the transportation problem? So remember, when we compute our CIGs, right, that is the net cost changes, right? The net cost change. When we compute it for each problem, right, we realize that when you compute this, right, we usually go for net negative values, right? We usually go for net negative values. So we see that if the resultants from the CIG prime or the net cost change is negative, then it means that when the non-basic variable or the empty cell, when it enters the solution or is allocated, it would reduce the cost because it is negative, right? When it's positive, it will increase the cost and therefore it will never go into the solution, right? However, what if it is 0? If it's 0, it means that it will not affect the Z function. That, yeah, the final cost will not be affected. It will reduce it, it will increase it. But what will it do? It will give us a new allocation strategy, right? A new allocation strategy. That's what it will give us. And therefore, we will then have to reallocate and get a new arrangement. The cost will still remain the same. However, the transportation strategy will change. So that is what multiple optimal solution does, right? Good. And what about maximizing a translation problem? So usually the translation problem, which we've done so far, right? We look at the objective function, which is cost, right? And therefore we try to minimize costs in a business. Nobody maximizes cost in a business. So there are, however, some problems where the objective function is to be maximized, right? What are special cases? For instance, when a mine equipment distribution network, they want to distribute mining equipment to the various mines, right? Then they look at which source, where am I moving it from, and to which of the destinations or which of the mines will need them, right? So you realize that the mine or the equipment distribution company may be looking at maximizing the profits. So you may have the profits of transporting from one source to another, or one from one warehouse to another, and therefore you may want to use that information to evaluate the situation, right? So in that case, he wants to maximize the transportation. But can we use the transportation tableau? So this is where is a trickish thing to do. So one of the solution procedure for the maximization transportation problem requires that the largest cell values, right, which represents the coefficient. So in this case, when you have the box and you have how much you allocate here, right, and you have the cost values here, right? Good. So the largest cell value, which is the profit coefficient transition problem, needs to be selected, and all other tableau cells values be subtracted from it, right? Be subtracted from it. So it means that we'll create a new tableau of relative cost values. So the problem can be solved according to the normal translation method previously presented. So what we do is that we subtract all the various costs from this largest value, right? So we take the large value and we subtract all the various costs from there. So for instance, we have this tableau, right? Let's assume we have this tableau. So to and from, right? So 1, 2, 3, 1, 2, demand, right? And we have our supply here. And this is 150, 130, 20. So 150 is balanced, right? So we have the various costs here, right? We have the various costs here. Let's say we have 8, 5, 3, 2, 10, and 4. All right, so if we have this typical transportation problem, right, as a maximization problem. So what we are saying we do is that we create a new tableau, right, and we allocate. So let me create that tableau quickly. Then when we create this, then we identify the maximum value in the original problem. So the maximum value in this original problem is this tableau here, right? So this is the original problem, right? And this is the transformed right? What we are transforming the problem into, right? So you see that the maximum C, so the maximum Cij, right, is the value 8, which is C11, right? It's 8. So what we do in the next transform value is to transform, pick the largest value 8, and no, sorry, the largest value is not 8. The largest value is 10. 2. You see, 2 is 10. So we subtract every cell from 10 so that we can have what we call relative cost value. So we'll say that 10 minus 8 is 2. 10 minus 5 is 5. 10 minus 3 is 7. 10 minus 2 is 8. 10 minus 10 is 0. 10 minus 4 is 6. So we do this transformation, and then we can now apply our known algorithms. That is the Virgil or the VAM, the Northwest, the modified distribution, the stepping stone. Then we apply this to solve our transportation problem. All right, so I hope this helps. Thank you very much for being with me throughout this lecture. And the next lecture series, we will look at the assignments problem, the assignment problem. So on this note, thank you. Have a good day. Cheers.